Hi everybody, welcome back to our video series on GCSE Maths. Today I thought instead of going through the paper and cherry picking which questions to do, I thought I'd just go through all of them. And as you know, I skipped question 27 right at the end. So I thought I'd do that one, and also as you can see we've changed the format. So as always, thank you very much to everybody for your support. Please feel free to critique me. Tell me what I can improve on. Tell me if you like this or not. Okay, so question 27 is on trigonometry. Trig. Okay. You've seen, well, hopefully we all know what the definition of sine of theta is. Opposite of hypotenuse. Cos of theta, adjacent over hypotenuse. And tan of theta equal to opposite over adjacent. But this lesson, if you like, is going to be broken down into two parts. The first part is we're going to explore what these things actually are, as in an intuitive sense, maybe draw them out, and then the second part will be actually getting around to answering the questions. In fact, the questions are quite easy to answer. I can tell you now that the answer to the first question is minus k, and the answer to the second question is k. So what we'll do is we'll spend this time just explaining why they are. So let's draw a circle, or let's draw as close to a circle as I can. That's close enough. And we have close enough. And we have these axes. This is the x-axis, and this is obviously the y-axis. Now this is called the unit circle, right? And the unit circle is characterized by the fact that it has a radius of 1. So wherever we put our radius, if I just change color quickly, here, 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 etc., etc., these lines all have a radius of 1. These lines are all of equal length, and that length is 1. Now, 1 centimeter, 1 meter, it doesn't matter. It's just 1 unit. Hence, unit circle. Unit is abstract. It's whatever we need it to be, but usually we just call it 1. So, as you can see, this line intersects the circle at some point. And this point here is some height off of the x-axis, which I will draw in red. It's some arbitrary distance far away from the x-axis, and is some arbitrary distance far away from the y-axis. But this is called trigonometry and trig 3. But this shape doesn't have 3 sides. So what we do is we quite simply just put the green line here. And now we have a triangle. And one last thing, we also have an angle. That's not very clear, but that's theta. So the question is, how does the length of the red line and the length of the green line change as that theta changes, as we extend this black line? Don't worry, I'm gonna get rid of those. How does the green line and the red line change? Well, for those of you who are maybe actually paying attention and not enjoying the time you have off, I'm only joking. You might already know what that red line and that green line is. think about the definition of sine, cosine, and tan. Sine of theta is equal to the opposite, the length of the opposite, divided by the length of the hypotenuse. But we know that the hypotenuse in this triangle here, this is equal to 1, because it's, as we said very clearly, the unit circle. So this just becomes O. In other words, sine of theta is exactly the length of the red line. And similarly, cos of theta is equal to the adjacent over the hypotenuse, which is just the adjacent, or in other words, the length of the green line. They're named as such because this length here, this line, this red line, is opposite to the angle. It's on the opposite side. Whereas the adjacent is literally adjacent to the angle. So now let's think, what will happen to the red line and the green line as we change theta? I'm going to draw some circles. Some smaller circles than that. So first of all, let's make theta really small. This is still length 1, and then we have sine of theta there, and we have cos of theta there. And again, if we make theta sort of normal size, well, not necessarily normal size. Normal is pretty subjective, isn't it? We have some sine theta there and cos theta there, and then we'll make theta very close to 90. And again, we have sine of theta here and cosine of theta here. And I'm just going to label, of course, we have angle here, here, and here. This is theta equal to 10 degrees. Theta equal to, it's about 30 degrees. And theta equal to about 60 degrees. So as you can see, as we have kind of, if you like, extended the angle of theta, if you like, opened up the triangle a bit, we can see that the length of the green line and the length of the red line both change. When theta is small, that cosine line is getting very, very close to being the length of the hypotenuse. In other words, 1. And as theta starts to open up and approach 90 degrees, this green line starts to get smaller and smaller. And the converse thing happens with the red line, with sine of theta. It starts off at 10 degrees, sine of theta is very, very small. It's almost 0. And then as theta approaches 90 degrees, that red line starts to get larger and larger, and then approaches 1 again. So they're kind of similar to each other, but opposites. What happens as theta becomes an obtuse angle? Well, we have to, this part's going to confuse some of you, but don't panic. It's quite easy once you get the sus of it. Because we're looking at this axis here, the x-axis, and the y-axis, and we can have negative x values and negative y values. We have this concept of the function sine of theta, or in other words, we have a concept of these lines having negative values. So because sine of theta represents, the red line represents, distance from the x-axis, if this line were to, for example, drop below the x-axis, then this would be a negative value. This would be less than 0. And a very similar thing happens to cos of theta. If cos of theta, if this line were to drop behind the y-axis, then this would be, again, less than 0. So what do I mean by this? Well, let me explain. If we take another arbitrary circle, there we go. Look at that. Oh, I didn't even know I could do that. So if we take this arbitrary circle and put, for example, this, and this, we'll draw a nice X on it. I can make them all straight now, can I? See, if we were to put all of these lines on there, we have this theta here, and then don't get confused. Then we have this theta. So this theta would be about 135 degrees. We always go anti-clockwise from the positive x-axis. And then we go this theta here. And then lastly, this theta here. Obviously, theta will get bigger and bigger, but it won't surpass it could surpass 360 degrees. But for the purposes of this, we don't really need it to go any larger than 360 degrees. But let's think about what the sine and the cosine will do. So in the first instance, we have this one in this first quadrant. That's what they're called. If we separate the this up, it's quadrant 1, quadrant 2, quadrant 3, and lastly quadrant 4. So if we look at what, for example, sine of theta is doing, sine of theta first, and then cos of theta, then we see certain properties. So in quadrant 1, they're both positive. They both form positive. The green line is to the right of the y-axis and above, and the red line, is above the x-axis. But in quadrant 2, here, we have this line is the red line is still positive, the red line here is still above the x-axis, so this is positive, greater than 0. However, this green line, this is less than 0 because, as you can see, it's to the left of the y-axis. And then again, down here, they're both negative because this line is now underneath the x-axis and therefore is less than 0. And the green line is to the left of the y-axis and is therefore also less than 0. And lastly, over here, this red line is still below the x-axis, so it's still 0. Sorry. No, that was right. But that green line is to the right of the x-axis, to the y-axis, and is subsequently positive. So the question is, what does all of this have to do with the question? Well, if I just complete the thing, greater than 0, we're now in a position to start mapping out what these functions actually look like. So if we draw a nice straight axis, there we go. Now I'll only do this for positive values because you'll see why actually. So as we open this triangle up from 0 to 90, we know that sine starts at 0. It won't go from between 1 and -1. It won't go any larger than that. So sine starts at 0 and curves up to about here. That's where you get the name sine from. Sine means curve, or something similar to curve in Greek. Hold on, there we go. But what happens at cos? With cos? Well, cos starts at 1, and as we saw, gets smaller and smaller. And then, what happens in the next quadrant? Here, sine of theta continues to stay positive but approaches 0, and cos of theta approaches -1. It's minus unit length. So in other words, sine of theta will begin to approach 0, and cos of theta will continue on. And then lastly, sine of theta again starts off at 0 and approaches -1. In other words, it will start to approach this line. And cos of theta will begin to approach 0. We'll begin to approach this length, then this length, then here. So we'll go a little bit like this. And then lastly, cos of theta approaches 1. And sine of theta again approaches 0. It's not very good. So this gives us sine of theta, how the length of these lines change as the angle changes, and cos of theta, Now let's make a few observations. Well, obviously, the most blatant one is that they are the same graph, just shifted over slightly. In other words, for example, sine of theta plus 90 degrees is equal to cos of theta. And one for the more maybe advanced among you, if you think about what the gradient does at each point of, let's take sine of theta. Here the gradient is a straight line and then slowly caps off and then becomes -1 and then caps off again. Well, think about it. What graph is equal to 1 at theta equals to 0 and then is equal to 0 at theta equals 90 degrees and then is -1 at theta equal to 270 degrees and then is 0 again at 360 degrees? Well, it's cos, isn't it? In other words, the gradient d sine theta by d theta is equal to cos of theta. I will omit the proof of this for the time being because it's a bit too advanced. Not to patronize anybody, if you don't need to learn it, I just wouldn't bother. But of course, I'm more than happy to show you that proof if you like. And now let's answer the question. Let's see exactly why we have, as I stated up here, k and -k. Well, let me just draw the cosine graph. Cosine graph does something like this, as we've investigated. We're told that alpha is an acute angle, so alpha is less than 90 degrees, and that cos of alpha is equal to k. Here is 180 degrees. I'm going to draw two regions onto the graph. I'll do them in a different color. I will do them in, here we go, light blue and dark blue. Okay, we have the light blue region here and the dark blue region here. At every point in the light blue region, so if I pick an arbitrary point here, there is, if you like, a corresponding point in the dark blue region here. Where whatever the value of the light blue is, so let's say for example that this is k, this in the dark blue region is the same distance away. In other words, the actual absolute magnitude, the length of the line, if you were to take them out, put them into an abstract space and measure them, they would be exactly the same. But because they're orientated differently, i.e. one has to be negative, hint hint, we have -k. Well, that looks very familiar, but why -k? Well, again, if I consider this whole notion of an abstract way to measure exactly the same length, if we say that this angle here, this is alpha, but more specifically, this alpha is actually 0. We start at 0 and we add alpha to it. We start here and we go along alpha distance. we could go along two units or three units, whatever, but we just go across alpha. Because I said here that the that this distance here excuse me, is the same. If I draw out again, this distance here, this is still alpha. That length there is alpha. They're the same length. If I were to draw them like this, maybe, oops, they're still the same length. They're both equal. And so, this length here, this point, if I do this just with a little bit of black in the middle there, that point is exactly, I'll do it in blue, 180 minus alpha, because we start at 180. Here we started at 0 and went alpha degrees to the right, but here we start at 180 and go alpha degrees to the left. But because they're corresponding, you multiply whichever one you get, you multiply by the other side, by -1. So in other words, we have this equality. We have that cos of alpha is equal to minus cos of 180 degrees minus alpha degrees. So k is equal to minus something, which tells us then that this minus something must be equal to k. I've just rewritten this. Divide both sides by -1, and we get that this something is equal to -1. Sorry, minus k. Hence, pardon me, hence minus k. And lastly, cos of 360 degrees plus alpha degrees. Well, as we can see, this graph resets itself every 360 degrees. In other words, it's 360 degrees periodic, which means, in conclusion, that cos of alpha degrees is equal to cos of 360 degrees plus alpha degrees, and so is just equal to k. So as again, thank you very much for watching. If you would like me to go into more detail about anything here, please do not hesitate to ask. If you'd like to see anything else, any proofs, etc., again, please ask me. Thank you very much for watching. Thank you very much for my